kids. All right, we're going to do a problem here. A proton is held 1 meter from a plus 4 microcoulomb charge. The proton is then released. What is the proton speed when when the separation is now 2 meters? And then just kind of a qualitative thing. What would the proton speed be different if both of the charges were released instead of just the proton being released? So we'll do the first part first. So hopefully you would look at this and go, hey, well, I don't know what to do, so I'm going to draw my picture. So if I sketch out what's happening, here's what's happening first. I have a 4 microcoulomb charge. I have my little proton right here. They are separated by a distance of 1 meter. And then later on, I have my 4 microcoulomb charge. I have my little proton here. They are going to be now separated by 2 meters, and my proton is moving that away. So hopefully you would go, okay, so they're like this, and then they're like this. So you should hopefully be thinking, especially with talking about speed, you should be thinking, hey, kinetic energy, so conservation of energy, so let's do conservation of energy. So you say, okay, so I drew my picture. At this point, I just have potential energy. At this point over here, I have potential energy, but it's going to be a different potential energy. Plus, I have kinetic energy, and there's no work done, so I'm just going to set them equal to each other, and then it's just a matter of plugging your stuff in and solving. The general equation for potential energy, even though like it's the 1 over 4 pi epsilon naught, remember that's just the same thing as K, so I'm going to have K, Q over R. Well, I should mention, if you look on your formula sheet, okay, you're going to see this. You'll see V equals essentially K, Q over R, and then you're also going to see U equals, okay, the V times Q, which is hence where I get that equation. Okay, so hopefully that makes sense where that equation come from. This is given on your formula sheet. This is given on your formula sheet. So there you go. Okay, so I get this equals this. So my new KQQ over some new R plus 1/2 mv squared. And then at this point, hey, I just got to plug stuff in. As far as what do I plug in, I'm going to erase it just so I can, or you can see it. Actually, I'll do it right here, just so there's room. This is going to be 9 times 10 to the 9th, okay, times 1 of the q's, 4 times 10 to the minus 6, times the other q. Charge of a proton is 1.6 times 10 to the minus 19th. All over 1 meter. Please, guys, be careful. You know, as this unit progresses, we're going to have all kinds of equations with K's and Q's and R's. So that's why it's important to write your general equation first, like I did, even though I just erased it, and then underneath plop your stuff in, okay? Over here, I'm going to have 9 times 10 to the 9th. I will have 4 times 10 to the minus 6, 1.6 times 10 to the minus 19th, all over 2, and then this is adding 1, and then the mass of my proton that is moving is 1.67 times 10 to the minus 27th kilograms. Again, it's on your formula sheet, so look it up. Hang on, my computer, wake up. All right, and then times v squared. So then you got to slam your numbers in, you solve for v. I think I already did this, and I got, assuming I did it right, 1.86 times 10 to the 6th meters per second. So, bam! How much fun is that? All right. So anyway, that's part A. Okay. If we're going to do part B, so let me erase so we can do part B. Part B is saying, hey, you know what? Now, okay, my after side, they're both going to be moving. So that's going to be moving also. So if you think about it, for my before side, I have potential energy. On my after side, I have potential energy plus the kinetic energy of the charge plus the kinetic energy of the proton. Well, if you just do it this simple way, you can see, hey, you know what? The same energy that I start with gets converted to more stuff. Therefore, less energy is going to get converted to the kinetic energy of the proton. Therefore, if they're both moving at the end, my proton is going to be moving slower. All right. Bye, kids.